In this lesson, we're going to be talking about the ideal gas law and its applications. So there's going to be three things we're going to do. We're going to do the molar mass and density of a gas using the ideal gas law, and we're also going to be doing gas stoichiometry. You just thought it was going away, it stays around, okay? So let's start with the ideal gas law being applied to molar mass and the density of a gas, okay? There are two equations that we're going to be able to use. Some teachers will not, they'll make you derive it. I'm just going to show you how you can just use these equations, okay? So molar mass is the first one we're going to talk about. And if I want to find the molar mass of a gas, I can take the density times RT and divide it by the pressure, okay? But we need to recall that density is equal to mass over volume, because we'll need that, because sometimes you'll be given a mass and a volume separately. And then if I want to solve for density, I can also use the molar mass of a gas times pressure divided by RT. And those are just different ways we plugged in some substitutions in the ideal gas law, and we come up with these two equations. And then we need to recall that molar mass is equal to grams over moles, because sometimes we'll have to calculate that. Okay? So let's do a couple of examples. For determining the molar mass of a gas, the next two examples are going to be on that one. And this one wants to know what is the molar mass of a gas if the density is 2.75 grams per liter. And when we're talking about density in terms of gases, it always needs to be grams per liter. And they gave us 729 torr and 60 degrees Celsius, which is pretty mean of them, because now we have to convert that stuff, because we have to match our R value units, remember, of 0.0821, which is liters times atmosphere over mole K. So we got to match our units to, obviously we always have to do Kelvin. So 60 Kelvin is going to be 60 degrees Celsius is going to be 333 Kelvin. But we're going to have to do a little conversion real quick for torr, because we need to be in atmosphere. So 729 torr divided by 760 torr in 1 atmosphere. And that conversion was from the very first lesson of gas laws. And so our torrs cancel out, and we need three significant figures because we started with that, and we're 0.959 atmosphere. Okay? So now we're just ready to plug it into this equation. Molar mass is equal to dRT over P. So now density they gave us as 2.75 grams per liter. R, of course, is 0.0821 liters times atmosphere, mole times K. And then our temperature was 333 Kelvin divided by 0.959 atmosphere. Atmosphere is going to cancel, and liters are going to cancel, and Kelvin is going to cancel. So I'm left with units of grams on the top, moles on the bottom, which is good because that happens to be the units of molar mass. And then I multiply the top and divide by the bottom, and leaving it in 2 decimal places for molar mass, like we've always talked about, my answer should be 78.40 grams per mole. In this question, we're still determining molar mass. And so we're going to use this MM equals dRT over P. And it says, what is the molar mass of a gas that has 754 milliliters and 12.8 grams? And then we're at kilopascals and 85 degrees Celsius. So 85 degrees Celsius is going to be 358 Kelvin. I see that my pressure, not in the unit we need, so we need to do that quick conversion. 102.5 kilopascal, and our conversion is 101.3 kilopascal is equal to 1 atmosphere. So that comes out to 1.01 atmosphere. Okay, so now I look and see that I need my density, and it does not give me a density. However, it does give me a mass, and it does give me a volume. And so I can use density is equal mass over volume, and I can calculate that. Okay, but because of my unit of liter on my R value, I'm going to need to do my density in grams per liter. So that is going to be 0.75 milliliters because I divided by 1,000. So 12.8 grams divided by 0.754 liters, excuse me. And then when I do that, I get 16.98, but I need 3 significant figures. So 17.0 grams per liter. So now I can plug in everything. 17.0 grams per liter, R 0.0821 liters times atmosphere, mole K, and then my temperature was 358 Kelvin divided by 1.01 atmosphere. So I get my molar mass. Liters cancel. Oops. Liters cancel. Atmosphere cancel. Kelvin cancel. Left with grams per mole. Multiply the top, divide by the bottom, and I get 494.71. Now, molar mass is one of those times where we don't really want to do the significant figures because we know molar masses are supposed to go to 2 decimal places. So we're going to do that. But if we were going to do in the decimal places, it'd be 3, so we'd be 495. Okay, I'm not that strict on that. I would take either one of those numbers actually, because right now I'm more concerned about the process. Density, this time we're going to be using that other equation. We're going to be solving for density, and density is going to be molar mass times pressure over RT. Okay, this time they tell us what's the density of 3 moles of gas at 2.3, so we get pressure and we get temperature, and that sample has this many grams. Luckily we don't have to do extra conversions because our pressures and temperature is already what we need them to be. However, we don't know what gas this is, so we don't know the molar mass, but remember molar mass, moles per gram, oh my goodness, let's erase that, is grams per mole. So they gave us grams right here, 15.9 grams. And then they gave us moles, 3 moles. So our molar mass is 5.30 grams per mole. So now we can go back up here and plug that in. 5.38 grams per mole times our pressure of 2.31 atmosphere divided by our R value, and temperature, which was 311 Kelvin. Kelvin cancels out, atmosphere cancels out, and liters doesn't, mole does. Mole. So we're left with units of grams per liter, which is the units for density. And so I multiply the top and I divide by the bottom, and I get 0.479 because I needed 3 significant figures, and that would be my answer for density. Here we have another density problem, density of oxygen. So molar mass times P over RT. Oxygen gas, remember, is O2 because it's a Brinkelhoff. So that means my molar mass is going to be 32 grams per mole. And they gave me everything but temperature that I need. So that's going to be in Kelvin. That's going to be 308 Kelvin. So now let's plug it all in. 32 grams per mole times the pressure, which was 1.23 atmosphere, divided by R, 0.0821 liters times atmosphere, mole times K, and then our temperature of 308 K. So we do all that math, we cross out our moles, we cross out our atmosphere, and we cross out our Kelvin, and we're left with grams over liter. and we need 3 significant figures. And so that would be 1.56 grams per liter. So that brings us to gas stoichiometry. Okay, so a couple of things we want to remember about gas stoichiometry. Okay, recall that the molar volume depends on the temperature and pressure, not its identity. So for the same standard temperature and pressure at STP, which was 1 atmosphere and 0 degrees Celsius, any gas is 22.4 liters per mole. So if we see a problem and they ask us about something at standard temperature and pressure, it's easy because we're just going to use that 22.4 liters per mole, like we did in regular stoichiometry, because we assumed it was all standard conditions, okay, STP conditions. However, if it's not at STP conditions, we're going to have to use the gas law, PV equals RT, to find the volume of 1 mole of gas at the conditions listed, okay? So let's do, I've got one of each to work, and then this lesson is going to be done for today, okay? So what volume of hydrogen is produced by the reaction of 36.5 grams of magnesium with excess HCl, okay? So this is just at standard temperature and pressure. So this is just a straightforward stoichiometry problem like we did in the stoichiometry unit. So we're going to start with 36.5 grams of magnesium. Oh my gosh, I forgot to balance the equation. Silly me. So we have magnesium plus HCl, and it's going to make magnesium chloride plus hydrogen gas. And of course, we're going to need to put a 2 there so that we balance it. Now we can proceed. So magnesium divided by its molar mass is 24.31 grams per mole. Now that we're in moles, we can go straight into our mole ratio. So we have 1 mole of magnesium makes 1 mole of hydrogen gas. And because we are at standard conditions, 1 mole of any gas is equal to 22.4 liters. So now we just do our math and we calculate that out, multiply the top, divide by the bottom, and we get 33.6 liters of hydrogen. So that was at STP conditions, standard temperature and pressure. But what if we're not at standard temperature and pressure? When we have to do something a little bit different, okay? So when we are not at standard conditions, like here, okay, because we are at 25 degrees Celsius and this many torr. So first thing we're going to need to do is say that temperature is going to be 298 K, which is not standard, and we're not in atmosphere. So we got to transfer to atmosphere. So we're going to do this. We'll do this right here. We're going to do 730.5 torr. Conversion factor is 760 torr. There's 1 atmosphere. And so we do that conversion, and that is going to be 0.9612 atmosphere, matching our sig figs to the original. Okay. So we're going to first calculate the molar volume at the new conditions that they gave us. So first is calculate molar volume. Okay. And molar volume is basically the volume for 1 mole. Okay. So that means N is going to be equal to 1 mole. Okay. So we're going to use PV equals nRT, solving for V. So we will have nRT over P. So 1 mole, our R value is 0.0821 over mole K times our temperature of 298 divided by our pressure of 0.9612 atmosphere. And so we get our molar volume to be 25.5 liters at these conditions, okay? Okay, at specified conditions. If we had different conditions, we'd have a different molar volume. So now, same problem, 36.5 grams, we have the same amount. So we still have that same equation we did earlier, magnesium plus it's going to be 2 HCl yields magnesium chloride and hydrogen gas. So same equation, same amount we started with, but we're at different conditions. So we'd start with that 36.5 grams of magnesium, just like before. Then we're going to divide by the molar mass of magnesium. Same mole ratio, 1 mole of magnesium to 1 mole of hydrogen gas. And this time, instead of using the 22.4, because we're not at STP, we're going to use what we calculated here. So we would do 25.5 liters per mole. And then 25.5, I said that backwards. And then we calculate that, multiplying the top, dividing by the bottom, then it's 38.3. Okay, liters of hydrogen gas. So that would be that answer. And that's the end of this lesson, and we only have one more for this unit.